What if the simple act of striking a match could echo across a world larger than any planet we call home? Imagine a single spark against the endless swirl of storms that have raged for millennia on a planet more massive than Earth. Would the flame roar to life or be snuffed out before you could feel its heat? This question carries the weight of a hypothesis that seems absurd, yet it forces us to confront the very nature of fire, atmosphere, and the limits of human curiosity. Jupiter is not a solid surface, but a colossal ocean of hydrogen and helium, layered beneath pressures that would crush a mountain into dust. Its upper atmosphere hovers at a chilling -145 degrees Celsius, while deeper layers climb to temperatures that exceed 30,000 degrees Celsius. In this exploration, we will dissect the hypothesis step by step. The instant the match is struck, the short-term shockwave through the clouds, the possible planetary scale ripples, and finally, the philosophical echo that such a tiny act leaves across the cosmos. First, let us examine what a match actually needs to burn. A flame requires 3 ingredients: fuel, heat, and an oxidizer, typically oxygen. Jupiter's atmosphere contains virtually no free oxygen. It is dominated by molecular hydrogen and helium, both of which are poor oxidizers for a phosphorus-based match head. When the match head is struck, friction generates a temperature of roughly 400 degrees Celsius, enough to ignite the chemicals embedded in the match head. However, in the thin upper layers where the pressure is about 1 bar, the heat dissipates almost instantly into the surrounding hydrogen. The reaction cannot sustain itself. The flame is quenched within milliseconds. The brief flash would produce a burst of photons in the visible spectrum, but the surrounding gas would absorb most of it, converting the energy into a rapid expansion of hot plasma. So the match dies, but the energy it released does not simply vanish. It sets in motion a cascade of physical processes that we will now trace. The sudden heating of a tiny parcel of gas creates a micro shockwave, a sphere of expanding plasma that pushes against the surrounding atmosphere. In an environment where wind speeds can exceed 200 kilometers per hour, this shockwave is swiftly torn apart, its shape distorted by the jet streams that dominate the planet's belt. Yet even a fleeting disturbance can generate acoustic vibrations that travel through the dense layers below, akin to a pebble dropped in a vast ocean. These vibrations, though minute, propagate through regions where pressure rises dramatically, eventually reaching layers where hydrogen becomes metallic. In those depths, the material behaves like an electrically conductive fluid, and any disturbance can interact with Jupiter's immense magnetic field, stronger than our Sun's, inducing localized currents. The energy of the original spark, though minuscule compared to the planet's total output, is momentarily amplified by the surrounding medium, creating a fleeting, localized brightening in the infrared spectrum. Now consider the short-term atmospheric effects. The sudden heat injection creates a pocket of hotter gas that rises, expanding as it ascends. This ascent can trigger a small, localized updraft, drawing in cooler surrounding gas. As the pocket cools, it may condense trace amounts of ammonia or water vapor, forming a fleeting, bright cloudlet that briefly catches the eye of a distant observer. Such a cloudlet would be indistinguishable from the countless storm cells that constantly churn across the planet. Yet, it serves as a reminder that even the smallest energy input can be woven into the tapestry of a giant's weather. If you find this line of reasoning intriguing, think about the broader implication. A single, human-scale action, when placed in an alien environment, becomes a catalyst for a chain of events that, while invisible to the naked eye, reverberates through the planet's complex system. What do you think? Leave your thoughts in the comments. But the story does not end with that fleeting cloudlet. To understand the full cascade, we must follow the energy as it travels deeper, through layers where pressure climbs beyond what any human could ever endure, and temperature rises to the point where even the most robust materials would melt within seconds. In those depths, hydrogen no longer behaves as a simple gas. It transforms into a metallic liquid, conducting electricity with astonishing efficiency. The brief pulse of heat from the match, although minuscule compared to the planet's total output, becomes a perturbation in this conductive sea. When the hot plasma expands, it briefly disturbs the surrounding metallic hydrogen, generating a localized electric current. That current, in turn, interacts with Jupiter's colossal magnetic field, which dwarfs even the Sun's own magnetic influence. The interaction creates a tiny, transient auroral flash, a whisper of light that would be invisible to the naked eye, but detectable with sensitive infrared instruments. In effect, the match ignites a microscopic, short-lived storm of electromagnetic activity, a reminder that even the simplest human act can echo through the most extreme environments. Now, let us consider the medium-term implications. The upward-moving bubble of heated gas, after reaching its apex, begins to cool and spread laterally. In doing so, it injects a modest amount of kinetic energy into the surrounding atmospheric flow. Jupiter's atmosphere is a dynamic, ever-changing tapestry of jet streams, vortices, and massive storm systems such as the famous Great Red Spot. While the energy contributed by a single match is infinitesimal, compared to the power driving those colossal structures, it nonetheless adds a minute perturbation to the turbulent cascade. In a chaotic system, even the smallest nudge can, over time, influence the evolution of larger patterns, a principle known as sensitivity to initial conditions. Imagine for a moment that 1,000 matches were lit simultaneously across different latitudes, each producing its own tiny updraft and electromagnetic pulse. The combined effect would still be a drop in the ocean of Jupiter's internal heat, yet the spatial distribution of those disturbances could seed subtle variations in cloud formation, perhaps nudging a nascent vortex toward a slightly different trajectory. In the grand scheme, the planet would continue its relentless churn, but the match-induced perturbations would become part of the statistical noise that shapes its ever-shifting visage. Turning our gaze farther outward, we encounter the realm of observation. A distant spacecraft equipped with spectrometers might detect the brief infrared brightening caused by the match's plasma, registering a spike in the local temperature profile, lasting only a fraction of a second. For scientists monitoring the planet's atmospheric dynamics, such a signal would be a curiosity, a data point that illustrates how external influences, however trivial, can be recorded against the backdrop of a massive, self-sustaining system. It also underscores the precision required to differentiate human-made signatures from natural phenomena in the data streams we collect. Beyond the physical chain of events lies a more profound contemplation. What does this thought experiment reveal about humanity's relationship with the cosmos? We often imagine ourselves as masters of fire, wielding the spark that has propelled civilization forward. Yet here, on a planet where the very notion of a solid surface is an illusion, that same spark is quickly extinguished, its flame smothered by an ocean of hydrogen that offers no oxygen to sustain it. The match becomes a metaphor for the limits of our agency when confronted with environments that operate on scales and principles far beyond our everyday experience. Consider the philosophical weight of that realization. If a single ember can be snuffed out almost instantly, what does that say about the fragility of human endeavors when placed in the vast, indifferent expanse of space? Does it inspire humility, prompting us to recognize that our technological triumphs are but fleeting blips against the backdrop of planetary processes that have persisted for billions of years? Or does it ignite a deeper curiosity, urging us to explore, to understand, and perhaps to find ways to harmonize our presence with the forces that dominate alien worlds? These questions are not merely academic. As humanity contemplates future missions that may one day send probes, landers, or even crewed vessels to the giant planets, the lessons embedded in this simple scenario become relevant. Designing equipment that can survive, operate, and perhaps even thrive in environments where pressure reaches tens of thousands of atmospheres and magnetic fields twist and turn with ferocious intensity requires a respect for the underlying physics that a match on Jupiter experiment illustrates. It reminds engineers that every heat source, every chemical reaction, must be evaluated within the context of the surrounding medium, lest we assume Earth-centric rules apply universally. Now, let us step back and weave together the strands of this narrative. The moment the match is struck, friction creates heat, igniting a phosphorus compound. The flame, deprived of oxygen, fizzles within milliseconds, releasing a burst of photons that are quickly absorbed by the surrounding hydrogen. That absorption transforms the energy into a rapidly expanding plasma, which in turn generates a tiny acoustic shockwave and a fleeting electromagnetic ripple within the metallic hydrogen below. The result is a brief, localized brightening in the infrared spectrum and a microscopic auroral flash. The heated pocket rises, forming a transient cloudlet that merges seamlessly with the planet's perpetual stormscape. Over the ensuing seconds, the disturbance dissipates, yet its imprint lingers as a subtle contribution to the planet's turbulent dynamics. In this cascade, we witness a microcosm of cause and effect, an illustration of how even the smallest human action can intersect with the grand mechanisms of a celestial body. It is a reminder that the universe is a tapestry of interwoven processes, where each thread, no matter how slender, has the potential to influence the pattern, however subtly. As we conclude this exploration, I invite you to reflect on the broader significance of this thought experiment. How does the image of a match flickering in the alien skies of a gas giant reshape your perception of humanity's place in the cosmos? Does it inspire awe at the sheer scale of planetary physics? Or does it provoke a sense of humility about the limits of our influence? Share your thoughts, because it is through dialogue that we deepen our collective understanding of the universe we inhabit. If this journey through fire, hydrogen, and magnetic storms sparked your curiosity, consider subscribing and giving this video a like. Your support helps us continue to delve into the mysteries that lie beyond our world, turning questions into discoveries. And remember, the next time you strike a match, imagine the distant swirl of Jupiter watching, a silent witness to the fleeting dance of flame and gas. The universe awaits our questions. Let us keep asking them,